Hello from Midpoint Bearing. Welcome to our online bearing training with a focus on lubrication. Today's training on lubrication runs approximately 52 minutes and is designed for the beginner to the intermediate. Now let's begin. Today our topics will be midpoint bearing overview, Bud's background, and then we'll jump into the bearing training on lubrication, and my topics will be what I call the facts of life, functions of lubrication, key items, and then we'll end the show with a wrap-up and contact information. So let's start with our midpoint bearing overview and Bud's background. Midpoint bearing overview. Midpoint Bearing was established in 1985. We are a distributor of bearings and power transmission products. We have 4 warehouse locations: California, Texas, Oklahoma, and Indiana. California is where our corporate headquarters is located. Midpoint Bearing specializes in 4 major industries: wind turbine repair, electric motor repair industry, steel mill equipment, and the pump repair industry. Midpoint Bearing is a factory authorized distributor for many fine products, including SKF, Koyo, NTN, Schaeffler, Nachi, Timken, CR Seal, Aegis, Benchmark Thermal, and many more. A little bit on my background. My name is Bud. When you have a name like William Charles Frable III, you want to go by something nice and short like Bud. I'm from a small town called Napoleon, Ohio. I served for 5 years active duty in the U.S. Army. Then I became a steel ruled die builder. Did that for approximately 7 years. During the end of that time, I started schooling and finished my mechanical engineering degree from Cleveland State University. 13 years at Koyo Bearing in the engineering department. And in 2012, I was given the opportunity to work for Midpoint Bearing. Our next topic is the beginning of our bearing training on lubrication, and the first section I titled The Facts of Life. Bearing lubrication. I'm going to start with the facts of life. Many times I've heard these questions: how long should a bearing last? That's a pretty loaded question, because how long a bearing should last is truly defined on its speed, its loads, and there's a lot of factors that go into how long a bearing should last. And then you hear, well, what is bearing life? The expected bearing life is normally calculated by an equation called the L10 equation. It is virtually impossible to predict fatigue. So what they did years ago is they did a statistical variation of individual bearing lives. What that means is they studied hundreds of bearings, maybe thousands of bearings in the exact same scenario, and looked at their failure rates and used that to come up with this equation to best predict this fatigue. Now, the issue with any statistical variation is that you always have a failure rate, and that's what our 10 stands for. So L10, that 10 is defining a failure rate of 10%. So 90% of bearings will achieve this number before fatigue failure. So, continued on the facts of life, I have here is the standard L10 equation. To calculate your bearing L10 life, you have a constant of 10 to the 6th, a constant of 60 times N, which is your rotational speed, times C, which is your basic dynamic load rating, over P, which is your dynamic equivalent load rating, raised to the power of little p, which is 3 for ball bearings or 10/3 for roller bearings. To calculate this P, you need this combined load equation, which is basically looking at, based on the application, how much of your radial and how much of your axial load will apply to your bearing life. And that creates your P, which goes there. And then when you have multiple bearings in a system, you use this wonderful equation here that throws all your different life calculations together to calculate a system life. Now, notice anything interesting about all these different life equations? Do you see lubrication anywhere? I bet you don't. Lubrication is kind of important, and that's why we're in this training today. So maybe I understated it just a little bit. Yes, lubrication is extremely critical to achieving your L10 bearing life. Looking at the pie chart in front of us, we see approximately 50% of bearing failures occur due to some form of lubrication issues. These lubrication issues could be from contaminated lubrication, over lubrication, under lubrication, and a plethora of other lubrication issues. Now, there are calculations out there that can take into account the cleanliness and different things on your lubrication to help zero in your life equation. The thing that is difficult in the aftermarket is a lot of these deeper information that is required is not available. Our next section we'll discuss is functions of lubrication. Within this section, I discuss grease or oil, and I also discuss additives. What does lubrication do? Lubrication reduces the friction and wear inside the bearing. It covers the rolling contact surfaces, that's the rolling element and the raceway surfaces, with the proper oil film. It separates and lubricates each part of the bearing. Carries away heat generated inside the bearing. Important note is grease stabilizes heat, oil can remove. So in this case, carries away heat generated. The carry away part is only done with oil. It prevents corrosion and contamination. This is not a new idea. It's been around for a long time. The picture we see below is estimated to be from around 2000 BC. It is thought to be the first record of rolling motion on some palace wall that I'm not going to try to sound out because I will pronounce it wrong and butcher it. But what we see here is a large rock being moved across the ground, and they are throwing rollers underneath it to help it roll, to reduce that sliding friction. Now, I may be right, I may be wrong, but this right here, these guys right here look like they're carrying a jug, which could be oil or grease or something along that point, that they could be either soaking the rollers in or the ground in front to help reduce friction as they try to move this big rock. Many times I get the question, what is better, grease or oil? It's really dependent on your application and what capabilities you have within that application. But on this particular slide, I like to highlight the 7 different items that can be looked at and split up as good or bad. And if you graded them, you would see that sealing device is showing grease is easy and oil is complicated. All the rest of these other 6, lubrication ability, rotational speed, replacement of lubrication, the life of the lubricant, the cooling effect, and filtration of dirt, all of these, the oil seems to win. So you would think in your mind, well, why don't we use oil all the time? And the reason for that mainly is this top one, being able to seal the lubricant, is the most difficult aspect out there. If you can't seal that oil, if you can't keep the oil cool, so you need a circulatory system or something along those lines, the grease is the easy option and wins out. This slide might be a little redundant compared to the previous slide, but what it's doing is it's breaking out a little bit more in depth on the oil lubrication instead of grease. The first bullet is saying it's usable at high speeds, the oil lubrication, because a grease has the thickener and it is a thicker type of lubrication. At high speeds, it may get flung out of the bearing or away from the rolling elements and raceway. Usable at high temperatures. Again, it would really go back to the fact that you can circulate oil and control its temperature by using some form of chilling system. And you can control your amount better in a oil system, and this allows you to have the ability to reduce bearing vibration. The next comment I thought was kind of silly, but I like it anyway. But this comment says, oil lubrication mainly used when grease lubrication cannot be utilized. Oh, glad you brought that up, right? Quite interesting. This slide points out two reasons why grease lubrication is widely used. The first one is no need for replenishment over a long period of time. What that is saying is that the grease life is fairly long. And the second is relatively simple structure can suffice as a sealing device. If you've ever owned an old motorcycle or an old car and had an oil leak, it was extremely difficult to stop that oil leak. What this is saying is that grease does not leak as easily and it can be stopped relatively simple. For example, in your deep groove ball bearings, you have a rubber seal or you have a metal shield. It can actually do a pretty good job of stopping the leakage. If that was oil inside of that bearing, the oil would just run right out from underneath that sealer shield. And that leads us into the next section of this slide, is there are two methods of grease lubrication. Closed, which means that it has a seal or a shield bearing. They have an advanced amount of fill from the factory, so they come factory lubed. Normally, you're going to see 25 to 45% fill. We'll discuss that a little bit later. Or you have a feeding method, such as a bearing in a housing with a grease zert, and grease is pumped into the bearing from the outside source. What makes up a grease or an oil? Both grease and oil start with a base lubricant or base oil, and then you add additives. And a few of them that I noted here are antioxidants, rust inhibitors, an additive for a stronger film, stabilizers, and anti-foaming agents. The difference between the grease and the oil is that the grease also has this thing called a thickener, which makes up a very high percentage of your grease. Why do you need additives? I use this slide to kind of define what these different additives I pointed out do. Antioxidant stops the gumming up of grease or an oil. I don't know your ages, but if you ever had like the first generation of like oil injectors or fuel injectors for your car, they always would get gummed up and they'd always complain about your gas, and you'd add an antioxidant to your gas to help keep that system clean. Rust inhibitors are fairly easy to understand. They stop rust. Additive for stronger oil film is to reduce wear. Stabilizers is used to prevent the change in state. Now that's not moving from one state to another, like going from Ohio to West Virginia or Kentucky. That is changing from a solid to a liquid to a gas. We don't want our oils or greases to go from that liquid form into the gaseous form because it will not do its job. The next one is anti-foaming agents. Again, pretty easy to understand. That is to keep the formation of foam in your system. This slide shows the properties of a few common greases. This first one here, Albanian number 2, when I was working for a bearing manufacturer years ago, Albanian number 2 was very common in the industrial OE, original equipment division. And at that point in time, 20 plus years ago, electric motors came in with multiple different types of grease. Two of the commons were a multi-temp SRL and a Chevron SRI number 2. Today, Polyrex EM is the standard in the U.S. electric motor repair market. Right, here's your Polyrex. Now, the reason for this was a study that was done by Baldor that showed that Polyrex EM outlasted all the other greases. This, in turn, had all of the major bearing manufacturers switch their aftermarket product to Polyrex EM. In my opinion, two major important parts for this. Number one is the temperature range. Although I've seen the Polyrex temperature range be different from different chart to different chart, the -10 to 170 on this particular chart shows a very large temperature range. The low end may not be as low as your SRI, or excuse me, your SRL, but it does overlap all of the other greases. The second one is your base oil viscosity at the high end. This is showing that at the high end, 100 Celsius or 212 Fahrenheit, we maintain a Centi-Stokes of 12.2. We'll discuss that on a later slide. Many times in failure analysis, I hear people talk about the bearing just catching on fire, and knowing that the temperatures that it would take to burn steel are extremely high, I figured I would look a little bit into the temperatures that would cause a lubrication to catch on fire. To best do this, I felt that I needed to define a few key items. First one is a flash point. This is the lowest temperature at which it can vaporize to form an ignitable mixture in air. But the key is this must have an ignition source. Auto ignition is the temperature where ignition occurs without a source. It's also called a fire point. So that is where it just bursts into flames. Flash points less than 60.5 C or 140.9 Fahrenheit are considered flammable. I've seen that number different on different places on the internet, but I'm just going to run with that. Now, looking at our greases, Mobile Polyrex EM has a flash point. Again, flash point means it needs a source, a spark to cause a fire. Does not go to fire until 204 degrees Celsius or 400 degrees Fahrenheit. Chevron SRI, 260 degrees Celsius or 500 Fahrenheit before it will ignite with an ignition source. So I decided to look at some things I thought were more flammable. So diesel fuel at 62 Celsius or 144 Fahrenheit, add a spark and you'll get a fire. Gasoline, this was kind of crazy to me. -43 C, which is -45 Fahrenheit, and you put a spark to it, it will catch on fire. So a bearing to catch on fire has to be even higher. I would imagine 800-900 degrees Fahrenheit for steel to maybe create a spark to cause the Polyrex to catch on fire. But by the time you get to that temperature, the grease would be gone anyway. So I thought this was interesting, so I thought I'd add it to my presentation. Our next section will be an item I called key items. Within key items, I will look at the correct viscosity, ensure we have the proper amount of lubrication is being used, re-lubricate at proper interval, only use compatible greases, use clean lubricant, and sealing technology. So the first topic we're going to cover under key items is correct viscosity. The slide in front of you shows required viscosity based on each bearing type at operating temperature. It's really not shown in the chart, but that's kind of key. So what this is telling us, your ball and cylindrical bearings at operating temperature need a minimum of 13 centistokes. Different type of bearings, like a spherical is 21, spherical thrust roller bearing 32, but in our market, electric motor, the main number to really stick in our head is that 13 centistokes for the ball bearing and the cylindrical roller bearing. If your objective is to really hone in or zero in on your minimum viscosity, you can use a chart. What we have here is the pitch circle diameter, and these lines here represent the RPM, and it results in our viscosity. So we'll look at a case here where we have a 6315 bearing operating at 1800 RPMs. So what we need to do is we need to calculate the pitch circle diameter. This is not the precise pitch circle, but it is an estimator that makes this chart operate properly. And what we do is we take an average between the bore of the bearing and the OD of the bearing. In this case, on a 6315, that's 75 plus 160 divided by 2, resulting in 117.5 and an operating speed of 1800 RPMs. Coming down here on our pitch circle, we want to find our 117 area. Being logarithmic, this is 100, this is 150, this is 200, so in this ballpark is 117. The lines coming this direction are our RPM. So again, we're going 1000, 15, 2000, so 18 is in between that segment there. And we'll run the lines together, and in this case, we show our result of 12 centistokes. Are any of you scratching your head and going, wait a second, on the last slide he said, yes, this does drop below the recommended viscosity for a ball bearing. So what we're going to do is we're going to use the higher of the two. So 13 centistokes is what we're going to look for. Now, simply by changing your RPM, we'll see the same bearing running 800 RPMs, running the same lines together, because our pitch circle does not change, higher RPM, we are now saying it needs approximately 25 centistokes. Now, midpoint bearing, we do sell some Polyrex EM, and we do have access to some other greases, but we normally don't recommend grease or oil. We normally sell what people ask us. So if you call your grease guy and you give him your operating conditions and you say, hey, I've got a 6315, I'm running at X RPM, I need a grease that can handle this many centistokes. And the grease guy is like, huh, what's that? Well, time to hang up and call the next grease guy. So your grease seller should be able to tell you that this grease at this operational conditions will maintain your centistokes. Our next topic under key items is going to be ensure the proper amount of lubrication is being used. ensure the proper amount of lubrication is being used. This number varies a little bit from manufacturer to manufacturer, but most bearing manufacturers fill their sealed and shielded bearings with approximately a 25 to 45% fill. Over lubrication can cause problems in your bearings because you have to review it simply as your rolling element is being forced to move through that grease. A lot of people go, but it's grease. It should make it nice and easy to move. But I like to try to think of it as running through water. If you're running on a beach somewhere and the water level is at your ankles, it's fairly easy to keep your speed and the amount of energy that is being exerted to run through this water. Now imagine if you were trying to maintain that same speed and all of a sudden the water was up to your neck. That is what you're doing to the rolling element inside of the bearing. So the easy way for me is to think of it as running through water, and what does that do? It creates heat generation. Under lubrication, what it does is it does not allow there to be the correct film barrier between the rolling element and the raceway surface. What this does is causes metal to metal contact, which increases friction, which does what? It creates excessive heat generation. This leads us to that big question that is always hanging out there. Which is worse, lack of lubrication or too much lubrication? Kind of a loaded question. They're both pretty bad. So we're going to take a little time and look at both. This goes back quite a few years now, but it's still relative today. Back in my bearing manufacturing days, where I worked for a manufacturer, what we did is we took a 6207 C3 bearing, we loaded it up with 3,500 pounds of thrust load or axial load. We set an operating speed at 4,000 RPMs. These numbers may seem high. The objective was not to overload the bearing and give it more than it's supposed to be able to take, but I wanted my test to not have to last 3 years. I was hoping to complete a test in a few days. The other thing that we did to this bearing is we washed it clean. There was no grease, no oil, no rust preventative, totally dry bearing. Being the geek bearing engineer that I am, after I had my understanding of what the conditions were, I took this information and plugged it into my handy dandy life equation. Crunched some numbers, and at the end, the standard life equation, which is shown at the right on the screen here, resulted that this bearing should last for 8 hours. Now I had to test it. What you see in front of you is the test rig, and I will play you a video. I did have to shorten it because I can't keep you for an extended length of time, but we'll see what happens. So I know a lot of you just met me and you probably don't want to call me a liar, but Go ahead, write down on a piece of paper how long you think that lasted. Go ahead, write it down. Little test versus you and your buddy. We'll see who gets the closest. How long do you think this bearing lasted? By the book, it was 8 hours. If anyone guessed 15 minutes, you hit the nail on the head. 15 minutes is only 3% of calculated life. I know I didn't mention this earlier, but this life equation, this L10 equation, is extremely accurate, even though it's so basic. We've seen bearings last 3 to 5 times longer than L10. It's a great indicator of a bearing will last this much or longer. 3% of calculated life. That's kind of hard to wrap your mind around. But when you look at the life equation, it doesn't consider grease or temperature. It assumes that you're taking all those factors into consideration. So now we're going to look at the flip side. We're going to look at too much lubrication. What we have here in this chart right here is time on the bottom and temperature on the side. I apologize that it's in Celsius, but we'll work through it. So what we're showing here is that a bearing can be relubed multiple times and maintain its operating temperature. So we remove the grease escape valve. We're running around 50 degrees Celsius. We pump in our new grease. We have a temperature spike to about 80 Celsius. Over time, it does settle back down to 50. So we try it again, spike up to around 80. Over time, settles back down a third time and a fourth time. So we're showing that as long as the grease valve is open, we're allowing the amount of lubrication to stabilize. The bearing temperature will go back to its optimal running temperature. The chart here on the bottom, which is B, is where we left the escape valve closed, or there was not an escape valve. Started again around 50 Celsius, pumped in our new grease. We did not spike to 80. We spiked to almost 110 Celsius. Over time, a little bit longer time, it did settle, but it settled at 90. So this is about a 40 degrees temperature rise over optimum temperature to where this thing is running. Just simple conversion for you. 100 is 212 Fahrenheit. So if you're running around 90, you're running around 195 degrees. In this case, 50 is going to be in the ballpark of 145, 150 degrees. So what's going to happen is you're going to shorten your grease life, which in turn shortens your bearing life. I know I mentioned this a few slides back, but it's so very important that why is too much lubrication a problem? And as I had mentioned, is to think about it as running through water. When water's to your ankles, it's very easy to keep up your speed, but if you run it up to your neck, it's very hard to maintain your speed. And what this does is it creates excessive heat generation. How long should we leave the grease valve open after we re-grease is a difficult question, because I can't give you an exact time because it's going to depend on the size of your motor. The simple answer is until the grease stops flowing. You're going to remove that escape valve, you'll pump your new grease in, the bearing will automatically push away what it doesn't want, which will allow grease to move out. And then once it stops moving, you want to close the grease valve. Now, everybody likes rules of thumb. Well, how long should that take? Again, size of the motor. But in most cases, we see about 20 to 30 minutes. The other question that comes up is, well, when should we re-grease? I always like to say, well, Friday after lunch. No, just kidding. Actually, you want to do it while the piece of machinery is either running, if you can safely, or warm. And the reason for that is if you do it when it's cold, your grease is going to be thick, and you pump in your new grease, it will actually channel through the old grease and find its way to the escape valve and out. So you're not pushing the old grease out. You want that old grease to be thinner, hot, so when you push the new grease in, it will push out or purge out the old grease. So has anybody here ever seen something like this before? Oh yeah, I'm sure you're chuckling and laughing and going, oh yeah, I've seen that before. It's funny to you and I, but it's not funny to the guy that has to clean this mess up. Motors run on an air gap, and that air gap helps with the efficiency of the motor. And in these cases, I think that grease might be affecting the air gap just a little. How does this happen? This happens when somebody has a grease gun and goes a little bit crazy. This happens when the confusion of how much grease goes into this motor. Some people might go, well, it takes 2 or 3 pumps of the grease gun. And people think, oh, you meant 2 or 3 tubes. Well, it happens quite often. The elephant in the room is obviously, well, how much grease do we put in the bearing? This is a difficult question to answer because it is determinant on the size of your bearing. The data plate that you see on the side of a lot of motors will specify X amount of grams should be added to each bearing. Now, how that is calculated is this equation that's on the bottom. This is a Bud Steak article that I've written. It's issue 10 that I really think you should go out and download and read. It goes a little more in depth. Well, these calculations can only calculate the free space or the space inside of the bearing. So that number, those grams that they show on that data plate, is for the grease to be directly injected into the bearing. It is virtually impossible for a bearing engineer to calculate from your grease zerk through your inlet tube to your cavity and then into the bearing how much grease you need. We can only do our calculation on the bearing only. Our next topic will be the relubrication interval. The chart on the screen in front of you is a fairly common regrease interval chart. Pretty simple to use, very basic. We have RPM. These curved lines here represent the bore of a bearing, and then A, B, C are your bearing types. We're going to use a 6210 bearing as our example. A little bearing basics here for you. The 6 designates that this is a deep groove ball bearing, which is an A, a radial ball bearing. The 2 is the duty series of the bearing. That's the ratio of the OD and the width. And the 10 at the end, you multiply times 5 for your bore. So 10 times 5 is a 50 millimeter bore. So using our chart, using an RPM of 3600, we find the 3600, this is logarithmic, so this is 2000, this is 3000, this is 4000, so somewhere between these two lines is 3600 RPMs. We're going to draw a line there, and then we're going to find our bearing bore at 50, 30, 40, 60, so 50 is going to be in the middle. So we'll go about right here. And we'll run those two lines together, and according to this chart, again, logarithmic, 2,000, 3,000, 4,000, we'll say about 3,800 hours. That's how often you should relube this bearing. The chart we previously looked at is focusing on motors running or equipment running under 160 degrees Fahrenheit or 70 degrees Celsius. Once you go above that temperature, your grease life is shortened. And this is a temperature correction chart, which is, again, very simple to use. All you do is you find your temperature that you are running, your operating temperature of the bearing, which can be difficult. And my example is I took my 3,800 hours that we got from the previous slide and assumed that we're running about 190 Fahrenheit. So 190 Fahrenheit gives us a correction factor of 0.5. So you take your 3,800 times the 0.5 and it changes our regrease interval to 1,900 hours. Our next topic is only use compatible greases. The chart in front of you is a grease or lubrication compatibility chart. If you go to the internet and search grease or lubrication compatibility charts, you'll find 50,000 different variations. Now, to me, what is interesting is try to dig deeper and find the background information on any one of those charts. It's virtually impossible to do. That information, that data is just not there. So looking at the chart in front of us, we will see a few of the compatible green bearing signs and then a whole bunch of the incompatible skull and crossbones signs. Now, when I look at this, regardless, I like to say, wow, that's a lot of red. If you did the math, this is about a 72% chance of failing. I don't think I like those odds. My soapbox stance is don't mix grease if you don't have to. It's just not worth it. Regardless of what any of these charts say, there's not enough background information. Just don't mix grease. Problem solved. To add a little insult to injury, what I have here is a picture that I took of a new motor, and the stickers that are on this motor make your life a little more interesting, right? This top sticker says, caution, bearing lubricant, SO Polyrex EM. Oh, great, I know what kind of grease is in there. Let me read what this next one says. Oh, kind of grease, multi-temp SRL, or lithium-based grease. Wait a second. Polyurea, lithium. Memory from the chart says those two don't like each other. So what grease is in this motor? I don't know. You got a quarter? Let's flip it and we'll try to find out, right? Not a good scenario to be in. One of these is incorrect. Notice this is what we were discussing earlier, the 18 grams. If this is a big 5 horsepower motor and you have 18 grams, do you think you're going to get past the inlet tube? Probably not. So that is where you'll see those numbers of the amount of grams into the bearing. Now, if you do run into a circumstance like this where you are unsure which grease is in the motor, the difficult part is if it's a sealed or shielded bearing, it will have Polyrex. All of the major bearing manufacturers use that as their standard aftermarket grease. So if you don't know what you have in there, how do you fix that? Well, it might cost you a little bit of grease, but a little bit of grease is a much better price than paying a warranty repair on a burned up motor due to mixing of greases. What I recommend is do the relubrication process 3 times in a row consecutively. So remove your escape valve, pump in your new grease till you see it coming out, run the motor until the grease stops flowing, and then do it a second time. Add grease until you see it coming out, let the bearing purge what it doesn't want, and then do it a third time, add your new grease. Once the flow stops, close that zert, and you should be good. Not a guaranteed 100%, but it's better than any scenario where you have mixed lubrication. This was a failure I've got quite a few years back, where you can tell that this grease is runny. I chalked it up to mixing of incompatible greases. It could have been water, but what I'm trying to display here is grease A and grease B, even if the base oils are known to be compatible. Remember the slide way in the beginning when I discussed the additives? So the base oils might work together, but do the thickeners, do the antioxidants, do the defoaming agents, and so on. So all of the bells and whistles that are added into your grease, are they compatible? Any one of them not being compatible can cause your grease to fail, drop in viscosity, either become soupy like this bearing that we see in front of us, or clumpy, where it will not lubricate the bearing properly and you will have a bearing failure. The next section is use clean lubricant. This one's pretty cut and dry. We want to make sure our lubrication is clean. Last thing you want to do is throw dirty, contaminated lubrication into your super expensive piece of equipment. Now, some of the little items that can be done on the service side would be making sure that the zert fit is clean before adding your new lubrication, ensuring that the nozzle or the tip of your grease gun is clean. Just in case there's dirt packed into the nozzle head, I always recommend pumping a little bit of grease out of the gun and wiping it away, just in case the head has compacted lubrication or contamination in the lubrication. Another thing that I like to tell people to do is use one gun for type of lubrication. So you're going to take your grease gun and you're going to note this grease gun is used for grease A, and that grease gun will always be used for grease A. Another small item, more goes into the over lubrication, is understand how much grease comes out of your gun for one full stroke of your grease gun. It's kind of a measure it in weight so you have a good idea of, hey, one pump of this gun is going to give me 15 grams. So it makes it a lot easier for you to calculate and understand how much grease you're pumping into the bearing. Our last section of key items is sealing technology. The image we have here is a bearing with a pressed steel shield, commonly referred to as a Z. If it's on both sides, a ZZ, or it could be a 2Z. Changes from manufacturer to manufacturer, but it is a pressed steel shield. Now, the shield does not contact the inner ring. There is a gap between the edge of the shield and the inner ring landing. This gap's small. It's actually gotten more controlled over the years, but when we're dealing with contaminations, a lot of particles are at the micron level, and they can still find their way through this gap, regardless of how tiny it is. That's another reason why the use of clean lubricant is so extremely important. Today, sealed bearings, which I'll show you on the next slide, have improved to where their efficiency or their speed capabilities are very close to the shield, which does not have contact. On this slide, I'm showing two versions, the Nachi and the Cuello. This is the Nachi and this is the Cuello. These are both called light contact or labyrinth style seals. These seals are both designed to have a very light amount of contact between the inner ring landing surface and the seal. Inner ring landing surface and the seal. This allows these sealed bearings to operate at a very high speed. In the electric motor industry, although we know we run at what we consider high speeds, in the bearing world, electric motors really don't run at extremely high speeds. In a lot of cases, the sealed bearing is more than enough to handle an electric motor application. Look at that. We've made it to the end. Wrap up and contact information. So my wrap up and contact information, my email is right there in front, bud@midpointbearing.com. If you have questions, comments, anything else that you would like to see, feel free to reach out and send me an email. If you would like to learn more, such as the Bud's Take that I showed you within this presentation on grease fill amount, midpointbearing.com/Bud's Take. I have multiple articles that I have written that can be found at that site. Lastly, I want to throw a special thanks out to all of our awesome bearing suppliers, because without their information and their charts and all the stuff provided in their books, I would not be able to give you this presentation. So again, thanks to all of our great bearing suppliers. Again, thank you very much. I'd like to thank you one more time for sitting in on my bearing training on lubrication. I appreciate all the support. If you're looking for a distributor who drives their business from knowledge through experience, look Midpoint up. We truly focus on honesty, integrity, and being your partner. We do not sell motors. We're not your competition. Midpoint Bearing. We appreciate your business. Thank you.